So a very good morning students. In this class we are going to discuss fast carry generation, and in previous class we discussed how to generate the fast carry and how to get the expression, and we have a 4 equation means. So we have to substitute the first equation in second equation, we get the following equation, so that we can generate C4 that is I which is equal to 0 and C4 which is equal to G3 plus P3 into G2 plus P2 and Gi plus Pi into G0 plus P3 into P2 plus Pi into Po into Co. Therefore, C4 which is equal to G plus PCO, where G which is equal to G3 plus P3 into G2 plus P2 plus G1 plus Pi plus Go, which is equal to P which is equal to P3 into P2 plus Pi P0. See, it is a quick evaluate this function. And this slide shows how to generate all the carries within an adder block using this previous equations. However, in order to reduce the complexity, a suitable approach is to implement say-bit 4 adder blocks with only C4 generated using fast generation. This is used as an carry into next 4-bit adder block. Within each 4-bit adder block, conventional RCA is used. So this is a fast carry generation block. So here we have a 4 half adder circuit, and 2 inputs are 2 outputs. Inputs are A0, B0, output is sum and carry. And 4 half adder means A0, B0, A1, B2, A1, B1, A2, B2, A3, B3. Similarly, we have a carry C0, C1, C2, C3, C4, and sum also S0, S1, S2, S3, S4. Likewise, we connect fast carry generation manner, and other ways to implement combinational logic. So we have seen how combinational logic can be implemented using logic gates, example and or etc. So however, it is also possible to generate combinational logic function using memory device using read-only memories. And ROM overview. So what is meant by ROM? Read-only memory. So it is a data storage device. Usually it can only read the data, but we cannot store the data. It is usually written in once either at manufacturer or using a programmer. So read at will. Essentially, it is a lookup table where the group of input lines, say n, is used to specify the address of the location holding m bit data words. And for example, if n which is equal to 4, then ROM has 2 power 4 which is equal to 16 possible location. And if m which is equal to 4 means each location can store 4-bit word. So that the total number of bits stored in m into 2 power n, that is 64 in the example very small ROM. So this is a ROM storage device structure. This is structure of ROM. So structure of ROM means what? How many data will be stored in ROM, and how many data lines and how many locations are there in ROM. So that is nothing but structure of the ROM. And we have a ROM example, 64-bit RAM. We have A0, A1, A2, 4 address locations and data lines D0, D1, D2, D3, D4, and address are the X, Y, Z and O, and here address in decimal, and 0 to 7, that is 00 to 1, from 000 to 111, and XY Z is a 000, 001 up to 111, and F is a flag 1111 and 0001. Data will be D0, D1, D2, D3. Design amounts to putting minterms in the appropriate address location. So logic simplification required. Useful if multiple Boolean functions are to be able to implement. Example, in this case we can easily down to 4, that is for each on output. The useful multiple Boolean functions are to be able to be implemented. Example, in this case we can easily do up to 4, that is for each output line. So reasonably efficient if lots of minterms needed to generate. and ROM implementation. It can be quite inefficient, that is become larger in size with only few non-zero entries if the number of min-terms in the function to be implemented in quite small. So device which can overcome these problems are known as programmable array logic, that is PAL, and programmable logic array is nothing but PLA. And PAL and use only record min-terms are generated using a separator and plane, and outputs from these planes are added together in separate plane to produce in final output. And this is a basic PLA structure. Here we have A, B, C, and the inverter A bar, B bar, C bar. So that input will be given to the AND plane. That AND plane output will be given to the OR planes. So programmed by selective removing connections in the AND and OR planes, controlled by the fuses and memory bits. So that OR gate input will be given to the OR gate, 3 OR gate. I mean the AND gate output will be given to the 3 OR gate, and the output of the OR gate will be F0, F1 and F2. This is a basic PAL structure, that is programmable array logic structure. And other memory devices is non-volatile storage is offered, ROM, and some other memory techniques, that is flash, that is data remains intact even when the power supply is removed. So volatile storage is offered by static random access memory, SRAM, and DRAM, dynamic random access memory. So RAM is nothing but random access memory. Random access memory means we can write both and write and read. In that RAM we have two types, that is static RAM and dynamic RAM. In static RAM we have a volatile storage, and data can be written into the readout from the SRAM but is lost once power is removed. And memory application. So memories are used in computer systems. The central processing unit CPU often makes use of buses, a bunch of wires in parallel, to access external memory devices. So address bus is used to specify the memory location that is being read or written, and data bus convey the data to and from the locations. So the memory, more than one memory device will often be connected to the same data bus. And bus contention. So in this case, the output from the data pin 1 memory was 0, and output from the corresponding data pin of another memory was 1. The data on that line of the data bus would be valid. So how do we do encourage from the data from multiple memories to be connected to the some bus wires and bus connections. So the answer is tri-state buffers or device drivers and control signals. A tri-state buffer is used on the data output of the memory device if construct to the normal buffer, which is in either 1 or 0. If the output, a tri-state buffer can be electrically disconnected from the bus, right, that is, it will be no effect or any other data currently on the bus, known as a high impedance condition. And this is a tri-state buffer. Here we have a symbol of tri-state buffer. We have a output enable OE which is equal to 1 and output enable which is equal to 0. So that is we have a bus line, so that we connect output enable 0 and output enable 1, and the functional analogy will be a bus line that will be 1 and 0. It will open the switch. It will be a open circuit, and close the circuit will be closed circuit, and it will be act as a switch